Hopefully things go smoothly today. It'll be the first time. I usually work on the whiteboard to work through some of the mathematics, which we're going to do for kind of half the classes to sort of work on the board. But today we're going to try to work from the document camera instead, and that has a couple of advantages. It's nice and big so you can see it. I won't be standing like in front of it. You guys have to give me some feedback because this is a little bit of a new way to do it. We'll see how smoothly or not it goes. And again, your sort of comments after lecture or right in the middle of lecture, like if you can't see anything that I'm writing or something like this, let me know. And we'll give it a shot. And the nice thing is that when the document camera is on, it'll project up here. It'll also be recorded. So then there is an archive for posterity and for your own purposes. Okay, so let's go ahead and get rolling. Obviously, there's slides up front again. I'll bring those for each lecture. Occasionally, if we don't get through the material, you'll want the slides from the previous lecture. Sometimes I toss those into the beginning, but probably good to bring those generally. A few notes just about some class business kinds of things. I did activate MATLAB for this class through CSNET. If you're in the School of Engineering, that probably means a little bit more to you than if you're in the PBM program. We haven't done this before, so I don't know actually how you guys can access MATLAB in this sense. Is there anyone from engineering that knows how MATLAB is going to be made available if you have it made available through CSNET?
You can either go to a CSLab
okay.
or in Voltaire,
yeah.
Or you can remotely log in.
Right, so I think if you run the VPN, you can VPN into one of the machines and then launch it remotely or something. There's some missing steps there, but Alborz has it. Okay, so at any rate, give it a shot. It should be available. It should be active. If you haven't set up a CSNET account, you'll need to do that. That's what that link is for. I think that'll work even for the biomedical physics students. It's just a function of who's enrolled in the course. So anyway, hopefully that gives you a leg up. If you don't have access to MATLAB, figure it out quick because I'm going to give some more example code today, but it's going to show up on your first homework assignment, which you're going to get on Monday. Monday? I think on Monday. So it's not that far away. So you want to get a little bit familiar with that. And then, of course, if you haven't, if you have zero familiarity with MATLAB, you don't even know where to start, where to begin, your first point of contact is going to be Mike, the TA for the class. His contact information was actually in the previous set of lecture slides. Otherwise, the website is up. The link is there. The slides, the video, and the code from last week are all there and should link. If there's problems with the links, let me know. The video recording went okay. There was a glitch kind of for the second half hour that hopefully we've got sorted out now. And have at it. I also linked some PDFs to some relevant reading material. So there's some chapter numbers that link to the Latimer book specifically, but there's also some extra PDFs that, because your life is full of infinite free time, you might want to look at those as well. I did actually read them. I got a little carried away. Anyway, okay. So just a quick summary from last week, the first lecture for the course. We basically talked about the construction of the B0 magnet, the main magnetic field for the MR system. And hopefully you now know that MR uses a superconducting electromagnet. Both of those things are important. And when it comes to actually building out the room itself, we have to build it out with copper shielding to keep RF energy from getting into the room. And we need to build it with steel magnetic shielding to prevent our B0 field from getting out of the room. So we need to isolate our system from sort of interfering with other things and from other things interfering with it, if you will. And these systems are built to really high tolerance, right? So the engineering standards are such that they're accurate to within about 6 microtesla over large sort of volumes in the middle of the scanner. So these are sort of part per million or something like a few parts per million accuracy in terms of the overall field strength. And it'll become a little bit more apparent why that matters so much later, but that's an important design constraint. We also learned something about sort of what kinds of currents and windings are needed to generate large B fields, and we hopefully know that we need a large amount of current that's going to course through the system sort of without needing to resupply energy into the system for very, very long periods of time. The field decays only a part per million per maybe month or something like that. Okay, so questions then just about sort of the mechanics of the course, access to course materials, MATLAB, or the first lecture? The other thing that I should point out is that we do have lecture on Friday. We're going to do that twice this quarter just to kind of stay on top of things, given that we have the 2 Monday holidays. Hopefully that doesn't present an absolute conflict for anyone, another class, a lecture, seminar, or something like that. But if it's a problem, let me know and we'll sort that. But otherwise, we will meet on Friday as well this week. Okay, so with that, we're going to get underway. Slides are up front if you didn't grab a copy already. They're also available, the color versions online. These I print out so you can hopefully sort of make notes as you go. So this is where we are, right? We talked about having this sort of outline for the course, or at least for a large part of the course. And we talked a little bit about magnetic dipoles, but not very much. We're going to talk more about that today. We talked quite a bit about B0, and in this context, we're going to talk about how we ultimately generate so-called bulk magnetization. So we know how to generate a B0 field. Let's learn something about magnetic moments and then understand how that gives rise to what we call the bulk magnetization. The bulk magnetization is what's effectively observable to us. We don't observe the individual magnetic dipoles of the hydrogen itself, but we observe billions and billions, Avogadro's number of these things in the imaging volumes and the things that we look at. Lots of guys helped contribute to this. We'll learn something about Joseph Larmor today, the so-called Larmor equation, which is fundamental to understanding MR. We will perhaps get to Leonhard Euler and Euler's equation. It's a way of using complex exponentials to describe vector quantities. It's a very useful thing in MR. I'm not positive we'll get there today. And we'll learn a little bit about Peter Zeeman and the so-called Zeeman splitting phenomena. So just a few of the sort of players in the field, if you will. It's important to think about sort of the main principles for the B0 field. What is it that the B0 field provides for us? And mathematically, we want to start laying down some groundwork for this. So we know the B0 field is a strong magnetic field, usually greater than 1.5 Tesla. And we said before that it's a Z-oriented field, where Z is the long axis of the scanner, sort of the cylindrical axis of the scanner. It's the axis that the patient slides in along, sort of head first into the scanner. And mathematically, we just say that that B0 field is some magnitude B0 multiplied along some unit direction. So I'll use the K vector as our unit directional vector along the Z axis, if you will. Sometimes I'll call it K hat, sometimes it's K vector, but same. And this will come into play today when we start looking at some solutions to some differential equations. We have to know what is our externally applied field, and mathematically it's B0 along the Z direction. Now, importantly, the B0 field helps us generate bulk magnetization, right? So the more B0 we have, the more bulk magnetization we have. And we'll see where that comes into play in a little bit when we talk about Zeeman splitting and we look at this so-called Boltzmann distribution of the spin system. What it really means is that the so-called bulk magnetization, this M vector quantity here, is really just the ensemble or sum behavior of a bunch of little magnetic dipoles. So we take mu to be the magnetic dipoles, and if we just add up a bunch of them, right, where we're adding from the first spin up to the Avogadro's spin, right, 10 to the 23rd spins, then we have something that we call the bulk magnetization, M vector. Now, interestingly, what we're going to mathematically get a handle on today is an understanding of how B0 forces, so to speak, the M vector or the bulk magnetization to precess. And it does so according to an equation called the Larmor equation. And the simplest description of that is just that the frequency of precession, omega, is equal to gamma times B, where gamma is the gyromagnetic ratio for the species of interest. We know what it is for hydrogen. We know what it is for carbon-13 or 31P or whatever else. And B is the externally applied B field, oftentimes just the B0 field. But we'll see lots of different working examples in the next few days about different B fields that we use in MR. The other important B field that we'll talk about relatively soon is a radio frequency B field, which we usually denote as the B1 field. But they're all just electromagnetic fields to begin with. Okay, so let's look at the actual principle of nuclear magnetic resonance. We have water molecules comprised, obviously, of 2 hydrogens and an oxygen, and we're just going to zoom in on one of these hydrogen nuclei. And it has some interesting properties that give rise to the NMR phenomena. The first things that matter is the fact that it's positively charged. It's a proton, after all. And in addition to charge, it has a so-called state called spin. We're going to talk about this more later. The consequence of having charge and spin is this thing behaves like a magnetic moment, meaning little hydrogen nuclei behave like itty-bitty, teeny-tiny bar magnets. And they align with some B0 field, that externally applied B0 field. when placed in it. So not only do we have spin and charge, we have spin and mass. And spin and mass gives us angular momentum. And that means as a top would wobble around or precess in a gravitational field, our magnetic dipoles will also precess, but in a different potential field. It's a B field that they precess in. And so these magnetic dipoles will have this kind of wobbling behavior, just like a conventional top as well. And the combination of charge and spin and mass taken together inside a B0 field means that our spin system, our individual magnetic dipoles, they're actually spinning on some axis, or at least this is the classical description. And as a consequence of being in the B0 field, they also wobble around. We're going to look at the mathematics of this in just a second. But what this ultimately gives rise to is the so-called Larmor equation and the Larmor frequency, which says that that frequency of angular precession is governed by gamma B0, which we just talked about. The gyromagnetic ratio for the thing that we care about, and the B0 field. So there's some sort of obvious consequences of this. One is that as the B0 is increasing, your omega is increasing. And higher frequencies actually give rise to stronger and stronger signals. So it's one way in which having a high magnetic field helps. Interestingly, and we'll see this in a second, but gamma could be positive or negative. And that just governs the handedness of the precession. It can be a left-handed precession, as it is for protons, or it could be a right-handed precession, as it is for, I can't remember, but it's in that table. Something has a negative gyromagnetic ratio. Okay, so let's talk a little bit more about this B0 field. We talked quite a bit about it last time, but just a few more comments about it. Mathematically, this is what I want you to have in mind. The B0 field, I probably should have just written this as, well, this is fine. The B0 vector field, it has a magnitude B0 pointing along the K direction, and we take the K to be this long axis of the scanner. And I should say that this is the so-called laboratory coordinate system. In a few days or sometime next week, we're going to talk about different coordinate systems. And we have the so-called laboratory coordinate system, which is you and I standing next to the scanner and describing mathematically how the spin system is behaving. The other possibility is you jump in with the spin system, which is precessing at 64 megahertz, and you say, okay, let's demodulate that and operate in the so-called rotating frame. We'll get to that later, but right now we'll talk about the laboratory frame. We're standing next to the scanner, mathematically trying to describe the behavior of the spin system. In either case, it turns out the external B0 field is just B0 along the K direction. One thing I want you to get out of this class is a sense for sort of the magnitudes of things, both in sort of their strength, but also maybe their duration, because we use a large number of maybe a wide range of different time scales, and we also use a wide range of magnetic field magnitudes. And so we have different units for this. We can talk in terms of Gauss, we can talk in terms of Tesla. The unit conversion is a little bit unfortunate. It's 10,000 Gauss per Tesla. It would be nice if it was 1,000, but it's not. But we don't really interact that frequently with magnetic fields. I mean, maybe refrigerator magnets is where most of us have some sort of like physical sense for magnetic strengths. Oftentimes what's pointed out is that the Earth's field is half a Gauss. That's fine and nice and useful for navigation, but it doesn't really give me a sense for overall magnitudes. When you talk about refrigerator magnets, then you're getting into sort of the 10 or 100 Gauss magnetic field strengths. And then, of course, you can get magnets that are much stronger than that, neodymium magnets that are maybe 1,000 Gauss or more. But when it comes to the B0 fields that we're talking about, the ones we really care about, we're talking about like 15,000 Gauss, right? So these are really strong magnetic fields, and you'll get a chance to sort of play with a magnet, play with one of our clinical systems in a couple weeks. And for those that didn't take 205, I'll give you a sense for how strong a 1.5 Tesla magnet is. Okay, so that's a fair bit about B0. Let's talk a little bit about the bulk magnetization, and then we're going to work our way into ultimately deriving the Larmor equation today. So we talked already about how the hydrogen nuclei behave like magnetic dipoles, and they do that primarily because of the fact that the magnetic dipole arises as a consequence of spin and charge. And the mass is important for giving rise to this precessional behavior, which we'll see. So we know the spin and charge gives rise to a magnetic moment. What's a magnetic moment? Well, it's just a measure of the strength of the system's net magnetic source, right? So how magnetic is the thing that we care about? And there's ways of calculating the magnetic moment for an individual dipole or an ensemble of dipoles, and that's in the Lauter rubric. I'll show you an equation for that a little bit later today. And all we really mean by the bulk magnetization, and I showed you this earlier, we just mean that the bulk magnetization is the sum of all the magnetic dipole vectors. Now, at equilibrium, what's the let's say we're talking about this patient lying here on the floor. They're full of water, of course. Those water molecules are magnetic dipoles. The hydrogen nuclei are, at least. What's the available bulk magnetization inside some region of interest when someone's just lying outside the scanner? What's the sum of all the magnetic dipoles give you? Just zero, right? They're just pointed in every which possible direction. There's no organization to their orientation. It's the B0 field that confers some organization to the system, which we'll talk about in just a second. So if we look at a conventional voxel, maybe 2 by 2 by 10 millimeters, this would be a typical imaging resolution for MRI, not particularly high, a little bit on the low side. You can see that as a consequence of being mostly water, you're going to have a huge number, Avogadro's number of spins that give rise to the bulk magnetization behavior for, a single pixel or a single voxel. So we're going to escape this concept of magnetic dipoles shortly and really just think in terms of the bulk magnetization. But we've got a couple more things to talk about first. Interestingly, it's not all spins that actually contribute to the measured signal. So you might think, oh, I've got 10 to the 23rd spins. They're all helping me generate signal, but it turns out it's only just a very small imbalance between what we call a spin up and a spin down state. And so it's a very small sort of parts per million number of magnetic dipoles that actually contribute to the overall measured signal. And that's a consequence of a phenomenon called Zeeman splitting, thanks to Pita. So what am I talking about? So this is just an example, right? We've got a patient lying next to the scanner. We define our laboratory coordinate system. Left, right is usually taken as X. Head, foot is taken as Z. And that leaves the anterior, posterior direction as the Y direction. And at equilibrium, meaning when the B0 field is off and you're just sort of flying there or in a scanner with no net field, the spins are just going to point in every possible direction. But something interesting happens when the B field is turned on, right? So we energize our coil, our magnetic dipoles actually orient favorably along the B0 direction. So one of B0's main functions is to polarize the spins and generate bulk magnetization. Now, the story is a little bit more complicated than this for reasons I just said. The problem is that you get spins in the so-called spin-up state as well as the spin-down state. And so they don't all perfectly align along the B0 direction. Some are anti-parallel. And in fact, it's really just a small imbalance between those two spin populations that makes any signal available. If it was a perfect 50-50 distribution, MR wouldn't exist. And there's this slight imbalance between the energy levels of the spin-up and spin-down state that means we actually have something that's observable. If you were, well, I'll talk about that in just a second. Mathematically, when we look at it, we're just saying when B0 is off, we have a bunch of possible spin orientations. And when we turn B0 on, you can occupy the so-called spin-up state, which is a low energy state, or the spin-down state, which is a slightly higher energy state. And as a consequence of this so-called Zeeman splitting phenomena, you have almost a 50-50 split of the spin-up and spin-down state. We can look at this mathematically. There's an expression that tells us what is the imbalance between the two spin populations. And so if we just talk about the number of spins in the spin-up state minus the number of spins in the spin-down state divided by just the total number of spins, that's approximately equal to gamma times Planck's constant times B0 divided by 2 times Boltzmann's constant times the temperature. Okay, so what are we really talking about? This expression here on the left-hand side is just telling us something like what's the percent of spins in the spin-up state. But instead of being a percent, it's going to be even lower than that. It's going to be in the sort of parts per million range. Easy to work with this expression. Most of these things are easily known. We know what gamma is for, say, protons, for H1. We know Planck's constant. We know room temperature, Boltzmann's constant. Pick a field strength of 1.5 Tesla. Plug it in. And what you find is that the difference, right, between the spin up and spin down state is only about 4.5 parts per million. So it's just a few spins in the spin up state relative to that spin down state that gives us any observable signal, or it's that ensemble behavior that gives us some observable signal. Now, in this whole expression that describes the Zeeman splitting phenomena, there's only a couple things that we can control. What are they? We can control B0. What else? Temperature, right? Everything else is a constant or dependent on the species itself. So this is the other reason that people are interested in higher and higher field strengths, right? As I increase B0, I increase the difference in the population of the spin up to spin down state. I get a larger and larger difference, if you will. And so if we push this from 1.5T to 3T, we'd end up at 9 parts per million. And that's going to give us more available bulk magnetization. So it's another reason that higher fields are of interest in MR. We're a little bit signal starved. We'd like to have more signal. No?
Are the spin-ups always better than spin-downs?
In terms of number, yes. So the other thing we said we can control is temperature. Obviously, if we're working in sort of solution chemistry or something like this, we can change the temperature of the thing that we're observing. If we're imaging people, we don't have that option, right? People don't want to be cooled or heated in any way that would be useful. And we're talking about a Kelvin scale anyway, so you couldn't really change this distribution in any meaningful way by adjusting temperatures for the kinds of imaging that we really care about. So we actually talked about this a little bit already. We said that the sum of a bunch of disorganized magnetic dipoles just gives us no net magnetization. When we turn on the B0 field and we have this distribution of spin up and spin down states that are really organized, we have some bulk observable magnetization that in principle will point along the Z direction. So we'll have some component of observable magnetization that at equilibrium points along the Z direction. We're going to dig into the mathematics of this a little bit more very soon. So I want to talk a little bit more about nuclear spin, because that's a concept that you may not have come across before. The idea of charge and mass is relatively straightforward. Everything has, atomic particles have charge, atomic particles have mass, and you're used to thinking of those as being inherent properties, right? You can't change the mass of some subatomic particle, you can't change the charge of the subatomic particle. Well, spin is another property, and it's an intrinsic property, meaning the atomic nucleus has spin or it doesn't have spin. It has different levels of spin or amounts of spin, but it's an intrinsic property. It just is. And the concept of spin it's a little difficult. We're gonna wave our hands a little bit today, and it was really forced upon the scientists by the experimental evidence, meaning that they were making observations where they said something's not right, something is not obeying sort of classical physics here. And that gave rise to the insight that the subatomic particles were behaving as if they had spin. Classically, we think of spin as literally being spin, but in a quantum sense, it's sort of this other sort of ephemeral thing. I want to make a distinction, too, between spin and precession, and maybe even an ensemble of spins. So we can talk about a bunch of spins, and we usually just mean a bunch of water molecules or a bunch of hydrogens that are bound to water. We usually call those spins. Now, there's also the intrinsic property of spin. It's an intrinsic form of angular momentum, meaning that the hydrogen nucleus has spin. It inherently has angular momentum. That angular momentum is not increasing, it's not decreasing, and you can't make it go away. It's just an intrinsic property. It's really a quantum mechanical phenomena. I'll show you a neat video about this. And there really isn't exactly a classical physics counterpart to spin. We can think of it as spinning like a top, if that's useful. That kind of gives you a little bit of leverage to understanding spin. The bottom line is it's kind of an interesting phenomenon. It's interesting that this underlies NMR. You can have a very successful life without ever really understanding spin. And everything in MR is going to work just fine, even if you still don't really completely appreciate spin. But I want to make a distinction too, that we don't use these words the same, but that's spin and precession, right? So if we want to take the classical spinning top phenomena, we have a top and I can spin it. It's going to be spinning along its axis, and if I flick it off axis, it's also going to be precessing. So we make the distinction between something that's spinning and something that's precessing. That's not the same phenomena. And our spin system can both spin and precess. Okay, so this is the standard model. We're not gonna dwell on this for very long. There's all kinds of subatomic particles, quarks, leptons, goes on and on and on. The only two that really matter, maybe for right now, is the so-called up quark and the down quark. And the only reason I want to point this out is give you a sense of maybe kind of where the spin is actually coming from. The thing we really care about is the proton. and the proton is really comprised of two spin-up quarks and a spin-down quark. And the sum ensemble of those three subatomic particles means you have a positive charge and you have a spin-half state. So I said before that spin has a magnitude, and you can't take it away, you can't increase it or decrease it, and the proton is a so-called spin-half system. You can be a spin-1 system, you can be a 5-half system, you can be a 0 system. It just depends on sort of what subatomic particles comprise the thing that we're interested in. Just as a different example, the neutron is two down quarks and an up quark, and so it has a different subatomic sort of composition than the proton. Proton's the only thing we really care about for this class. Oh, there it is. Yeah. So watch this. This is totally cool. So not only is the music great. Okay. So this is a nice video that I got off of the web. And I said before that spin was sort of forced on us by the scientific experiments, right? So this is a really nice video of the so-called Stern-Gerlach experiment, which was going almost 100 years ago, right? People were sort of confronted with these strange behavior, if you will. So let's have a look at this so we can talk about it if we need to. So just a north-south field. And we're going to launch conventional magnets through it, little tiny magnetic dipoles, like bar magnets. We're going to launch them right through that field. And it goes up. Then it's sideways, goes straight, flip it upside down, it goes down. So depending on its orientation, it's going to land in different places, just as it interacts with that field. Okay, maybe not surprising. It's going to get interesting. Now we're going to launch hydrogen nuclei through. Goes up. Goes down. Up. Up. So imagine how perplexing this is, right? To a scientist who's saying, what the heck, right? This is not what I expected to see. I expected to get a nice uniform distribution, and I get this very bimodal distribution. Gator burger. Sorry, I'm trying to get through that. There we go. So what's the point? The point is that there was experimental evidence in that Stern-Gerlach equation that something else was going on. And the spin state for the hydrogen nucleus could only be one of two things, spin up or spin down. You couldn't have the sort of spin in the perpendicular state that landed straight in the middle of that distribution. With a conventional magnet, you could change its orientation, launch it through the field, and its interaction would have it spraying out somewhere along that sort of plus-minus axis. With the hydrogen nucleus, you fire it through, it's only spin up or spin down. There are no other possible states, right? And half of them end up to the top and half of them end up to the bottom and nothing lands in the middle. So there had to be something else about these particles that was causing that. And ultimately it was called spin, and then that's either a good word or a bad word. But that's the property of spin. Now, every spin system, hydrogen, carbon-13, whatever, has a so-called nuclear spin quantum number that's knowable. The nucleus is only going to be NMR active if it has non-zero spin. If it has zero spin, nothing to observe, we just move along. So how do we know what the value of the spin quantum number is? Well, that depends on sort of the chemistry of the thing that we're trying to observe. If the nucleus has odd atomic mass number, it's going to have half integral spin. And that's the system we really mostly care about, right? So a spin half system like H1 is the one that we're observing mostly. But you can also have, like I said, spin 3 half systems or spin 5 half systems. As long as they have an odd mass number, you're going to have half integral spin. Now, it's possible to have zero spin, like I said. If you have an even mass number and an even charge number, you're going to have zero spin. So things like carbon-12 and oxygen-16 are not NMR visible, if you will. You can also have nuclei with even mass number but odd charge number, and there you'll have integral spin. So you'll have a spin 1 system. I think nitrogen is maybe a spin 1 system 2. I can't remember. Still NMR observable, if you will. We threw together this chart. I threw this up last time. So it's just a table of, a bunch of different NMR active nuclei, or in some sense inactive nuclei, right? Carbon-12 is not NMR active. It has 0 spin, and consequently there's no observable gyromagnetic ratio. No reason to memorize this whole thing. I'll point out, there it is, nitrogen-15 has a negative gyromagnetic moment. So it's going to precess in the right-handed sense relative to protons, which precess in the left-handed sense. All right, so let's talk a little bit about this gyromagnetic ratio. It showed up in the table before and in the previous lecture, and it's a really important parameter for us because it's nucleus specific. Of course, we care about hydrogen, so we know and we'll memorize that hydrogen's gyromagnetic ratio is 42.57 megahertz per Tesla. It's a physical constant. It's unique for each NMR active nuclei. And importantly, we're going to use this expression in just a little bit. It's the ratio of the magnetic moment to the angular momentum. Okay, now that's not an obvious statement, and it's not derivable, it's empirical. This is observed. So the magnetic moment is equal to the spin angular momentum through the gyromagnetic ratio. It's difficult to have an intuition for that. This is one of the few expressions that we have to just kind of, by fiat, shove into our brains. Importantly, that gyromagnetic ratio, as we'll see, is going to govern the frequency of precession. And we're going to talk about the Larmor equation, which describes precessional behavior. We're going to see how gamma is important in that expression. We'll occasionally, depending on what we're working with and what we're doing, you might see gamma bar instead of gamma. I apologize if I mix up my gammas and my gamma bars. Lots of people like to not be responsible for factors of pi and minus signs and things like that, right? So we'll do our best, but just to be clear, gamma bar is actually gamma by 2 pi. Okay, so what are the implications of spin? You've gotten some sense for this already. We talked about how spin and mass are important for giving rise to spin angular momentum, and how spin and charge are important for generating a magnetic dipole. And both of those things taken together give rise to the underlying NMR phenomena. So here's just sort of a classical description of what's happening with a hydrogen nucleus. It has spin angular momentum. If you want to think about this as a spinning mass, as a classically spinning mass, that's fine. Maybe it has some radius at which the mass is acting, and it has some velocity of rotation. And we're gonna use that shortly in deriving the Larmor expression. So that's why I present it here. And the spin angular momentum is just equal to the cross product. This is coming hopefully from a physics class that you took within the last couple years. But it's just the cross product of the radius, right? So we have some radius vector and the underlying momentum. The momentum is just the mass times the velocity vector. So hopefully this expression is one you've seen before. We're going to work with this some today. And you'll see already that here we have the spin angular momentum entering in, sort of tied to some physical parameters in a very sort of classical physics description. And that's going to relate back to that expression we had a second ago about mu equal to gamma s, the other way around. We also built this sense, hopefully already, that the combination of spin and charge gives rise to an underlying magnetic moment, or a magnetic dipole moment. It has units in terms of joules per Tesla, and it's really a measure of the strength of the system's net magnetic source. So we're talking about how magnetic the underlying dipole is. And if you want to conceptually, you can think of this spinning charge as behaving like a little tiny itty bitty bar magnet. And again, in just a second, we're going to work on the board, so to speak, and we're going to escape this idea of having an individual magnetic dipole and start working in just the bulk magnetization, in terms of the bulk magnetization. We should also remember, because this is going to come up in just a second too, something about a B field. We can think of the B field as being a vector quantity. It has a magnitude, it has a direction, and it can exert a magnetic force on moving electric charges and on magnetic dipoles. So we're going to talk about the interaction of a magnetic dipole, which is the hydrogen nucleus, and the external B0 field, and show how that gives rise to so-called precessional behavior. It's important to remember that there's a torque that's exerted when a magnetic dipole is placed in the presence of a B0 field. So the B0 field exerts a torque on the hydrogen magnetic dipole moment. And this is the sort of classical picture you might have in mind. There's some magnetic dipole that's behaving like a little tiny magnet, and will be forced, we'll show you, it'll be forced to precess about the B0 field as a consequence of a balance of momentum. Okay, so where we're headed with that as background is an understanding of where this Larmor expression, or this Larmor equation comes from. We know, at least by just sort of having heard that B0 forces the bulk magnetization to precess. It's going to precess according to the so-called Larmor equation, but it's maybe not obvious where that comes from, and that's what I really want to talk about. The things that we're going to do again, of course, is take into consideration the spin and charge aspects of the system and the spin and mass aspects of the system, and show how that gives rise to this NMR phenomena. And this is the sort of basic outline of how we're going to work through this. We know that the spin angular momentum was just the cross product of the radius vector and the momentum vector. We had an expression that told us that the magnetic dipole moment was equal through the gyromagnetic ratio to the spin angular momentum. We're going to work with this expression. We're going to differentiate this expression. We're going to remember that there's a torque exerted on a magnetic dipole in the presence of a B0 field. And this is going to give rise to some equations for which there are solutions, one of which is bears out the Larmor expression itself. Okay, so this I'm going to switch over to the dock camera here, and with any luck, this will work relatively smoothly. I'll tear the screen out of the ceiling. Should get some groovy music to play while I'm getting set up. Oops. I'm writing over here. Look at that. You can certainly see my hand. Okay, we'll see. You guys will let me know how well this works. So we started with an expression just a second ago where we said that the magnetic dipole was equal to gamma times the spin angular momentum. Right? And all I'm going to do is differentiate, kind of rearrange things a little bit and differentiate with respect to time. And so then I know that ds dt is equal to, I'm going to bring the gamma over to the other side, d mu dt. Fair enough? And we're going to need this in a second. We don't need it quite yet, but we're going to need it in a second. The other expression that we had was that the spin angular momentum was equal to the position vector of where the sort of mass of this thing was located times the mass itself and the velocity. That's just a sort of classical physics description of spin angular momentum. Now, we need to sort of link some terms together. What I'm going to do is differentiate this thing on both sides with respect to time. So I get easily ds by dt. Now, on the right-hand side here, I need to use the chain rule, right? Because I've got two terms there. So the first thing I'll do is differentiate dr with respect to t. And that still has to be taken the cross product with m and v. And the next thing I'm going to do is hang on to my r vector and differentiate, take the cross product. M's just a constant, so we don't care about that. And we get dv dt. Okay? Just taking the time derivative using the chain rule. So the next thing is to recognize that this vector, the time rate of change dr dt vector, is actually parallel to the velocity vector. And if two vector quantities are parallel, what's their cross product? Just 0, right? So that means that that first term goes to 0. So I can, let's do it this way. We can drop this term out to 0. And I'm just left with the second term. We know that the time rate of change of the velocity is just the acceleration. And so we can just write that ds dt is equal to r cross ma. Nothing too terribly exciting here. You may know where this is headed already. We know that mass times acceleration is just a force, so we just have the radius vector cross product with the force vector. And what is that called? That's just called, I heard someone say it, that's just a torque, right? And so we have force acting at a distance, and that gives rise to a torque. And so at the end of the day here, we just have that the time rate of change of the spin angular momentum is a torque. Now, remember, I said a second ago, I said that there's a torque that arises as a consequence of the magnetic dipole being in the presence of the B field. There should be a gamma there, right? No, the gamma shows, sorry, gamma shows up later. We know that a torque just arises from the mu cross gamma B. Just a second ago, borrowing from, say, this expression here and bringing it over, we know, for example, that ds dt, because we're substituting in this bottom expression here, right? That just means that our ds dt is also equal to mu cross b. We can rearrange this a little bit. Wait, I need a gamma now. Yeah. We're going to... this left-hand side here just is 1 over gamma d mu dt. That's coming from the expression that's shown, the second expression that we had. And we still have that this is equal to mu cross. What's the point? Well, we just want a neat little expression that says that the time rate of change of the spin of the magnetic dipole vector is just mu cross gamma. And we could call this the equation of motion. We will call it the equation of motion for magnetic dipole. Okay, so not too crazy yet. All we've done is took some time derivatives and made some substitutions, but we have an expression now that tells us what's the time-dependent behavior of our of our magnetic moment in the presence of a B field. The B field is a vector quantity, so we have to be able to write down what that B field vector actually is. We have to know something about gamma, and then we can start doing things like solving for mu of t. So our ultimate goal would be to say, well, what is mu of t? Now, I said a second ago, we don't really care about the magnetic dipoles themselves. What we really care about is the bulk magnetization. And so the next thing that I want to do is just re-express this in terms of the bulk magnetization itself. Is that okay? We're good? I think you guys can do this faster than I can, but that's okay. Okay, so we said earlier in the lecture, we said that the bulk magnetization rather was just the sum from n equals 1, the first spin, to the total number of spins of the magnetic dipole moments themselves. Maybe mu pi. Let's differentiate this with respect to time easily enough. We have dm dt. We see that we have a connection here between the magnetic moment dipole and the bulk magnetization. We want to link that back to the expression we had at the end for the equation of motion. So taking the derivative with respect to time,
easy enough because there are not a lot of variables here. So it's a sum over from n equals 1 to the number of spins, and now we just have the time rate of change of the magnetic. Remember just a second ago, I'll write it down, you guys have it in your notes already, that we said that d mu dt was just equal to mu vector cross gamma b. And now I have an expression, I have a set of expressions that I can use to replace this in terms of the actual bulk magnetization. So if I want to, I can take this expression here, I can sum across both sides. I'm just going to add up from I equals 1, or sorry, what I have n, from n equals 1 to ns of my d mu dt. I'm going to add up a bunch of spins on the right-hand side too. This whole thing, e vector, I should add them all up as i's cross gamma b vector. And I know what this quantity on the left-hand side is. I can get it from right up here when I did the differentiation. So I know that just by substitution, this left-hand side here is dm dt. And I know that my right-hand side, again, just by substitution, there's no summing up exactly over the gamma b0, the gamma b term. And so I can just use the first expression that I had to say that this just looks like m vector cross gamma b vector. And so finally, what we have here is the equation of motion again. For the bulk magnetization. What coordinate system were we describing all of this in so far? We talked briefly about different coordinate systems. This is what we call the laboratory frame. Now, this expression actually gets a lot simpler when we work into the rotating frame, and that's part of what will motivate us later to change coordinate systems. The mathematics gets a lot simpler, but for right now, this is a description now of the magnetic vector, the bulk magnetization vector, as a function of time, right? How's it changing as a function of time when there's an ensemble of magnetic moments placed inside a B field that have a given gamma? Question or no? Okay. So that doesn't answer the question that we're really after. That just gives us the first point of entry, which is to say we now have a differential equation. It's a vector. It's a differential equation that depends on a vector, the bulk magnetization vector. We want to link this up to the Larmor equation, but to do that, we have to do a little bit more work first. So this is the equation of motion for an ensemble of spins. We sometimes call an ensemble of spins isochromats. Spins that are all precessing at the same frequency are called isochromats. And this is a very sort of classical description of the bulk magnetization's behavior. Now, that's nice to have a set of differential equations that describe the spin behavior, but it probably doesn't have a lot of meaning until we talk about specific solutions. So one thing that we'll do now is actually work towards a general solution for what is the bulk magnetization doing in a B0 field. I want to make a distinction before we sort of get into that, and that's the distinction between so-called free precession and forced precession. Free precession is the precession of the bulk magnetization vector about the static magnetic field after pulse excitation. So we put spins in the B0 field and we act on them in some way. Maybe we have an RF pulse that acts on them, perturbs the system, and now we're no longer perturbing the system. They're just going to freely precess in that B0 field and go back to some equilibrium state. So free precession of the transverse magnetization, specifically at the Larmor frequency, is what's responsible for the detectable NMR signal. So free precession is a really important state for us, if you will. But forced precession is also really important because we have to be able to perturb the system. It's not interesting just to put water in the scanner. We want to act on the water force it out of its equilibrium state, and then observe it as it's recovering in a way that we can actually get a detectable signal that gives us something interesting to look at, like an image with contrast. So what's forced precession? Well, that's the precession of the bulk magnetization about the excitation RF field. We haven't talked about the radio frequency pulses very much yet, but they're the radio frequency, the electromagnetic field that's used to push the spin system out of its equilibrium state. And then it's going to freely precess back to its whatever the equilibrium state is in the presence of just the B0 field. Lots of different sort of special cases here, and we're going to work through answers and solutions to a bunch of these over the next sort of many weeks. What's really nice about MR in some ways is that there are some really nice governing equations, and we can work really well with those governing equations. And you'll do that both in your homework, and we'll do it together in class a bunch. But I think it's maybe amongst the more challenging concepts to get in MR is tracking or keeping track of what the bulk magnetization is doing during the NMR experiment, if you will. So the different special cases that we could talk about include free precession in the laboratory frame or forced precession in the laboratory frame. And that's, again, that coordinate system that's anchored to the scanner. Later, we'll make a transition into the so-called rotating frame. It's sort of like getting on the merry-go-round, right? And making the observation of what's happening when you're on the merry-go-round, which is the rotating frame, versus standing next to it. And those four special cases are all without the specifics of relaxation. We'll introduce relaxation, I think, sometime next week. And that just means that right now we're talking about kind of somewhat specialized circumstances, meaning we act on the system and it doesn't relax, right? Why would it do that? Well, either the relaxation time constants are really long so that it doesn't sort of get back to its native state on any time scale that's observable, or the time scale of the event that we care about is really, really short relative to the relaxation time. So free precession without relaxation is important. That's actually largely how we can describe what's happening to the spin system during RF excitation, something that we'll get more into a little bit later. What we're going to do now is go back to the board, so to speak, work through a solution to that equation of motion, because I think that'll give us some insight as to what's actually happening to the bulk magnetization vector in the B0 field. So specifically, right now, we're going to talk about free precession, so just the spin system, precessing in the B0 field, specifically described in the laboratory coordinate frame, and without giving consideration to relaxation effects yet. We'll get to making it more complicated as we go. Sorry for that. How's it working with me writing here? Is it viewable, seeable? Is it better than if I'm on the actual board? You can say no. It's more fun. It's a pretty cool system, right? I mean, I will have to admit that. The problem with when you're working on the board, you guys have all been there, but I'm usually standing in front of it while I'm writing, right? And so you can't, oftentimes half the class can't see even what I'm writing. So the only downside is you have to look at a magnified view of my hands. Okay, so where were we? Well, we had this equation of motion. You guys have it down already, but I'll write it again. That the time rate of change of the bulk magnetization vector was just equal to the magnetization vector itself, cross product with gamma times the B field. Now, this isn't so bad. It's a pretty simple expression to write down. This is going to later give rise to the Bloch equation. So if you've studied MR at all before, we're going to add a bunch of terms over here that are related to relaxation, and things will get a little bit more complicated and arguably a little bit more interesting. Let's talk about this B right here. What is it? In the simplest case of just an MR system, we can actually write down a vector quantity for B.
B0.
Say it again, Jason.
B0 field?
Yep. And so we can write it, we can just say that our B vector, right, is just equal to B0. That's its magnitude, and it points along, say, the k direction. Okay. Now, what we actually have in that equation of motion expression is a system of differential equations, right? It's a little bit complicated because those are m as a vector quantity, right? Even if I didn't write it as clearly as I could. But we're going to use this specific B field because it's the one that's of interest to us right now. And we're going to be able to write out this system of differential equations in a way that gives us a little bit of traction. And so the way I'm going to do that is I'm going to say that dmx, where am I? Yeah, dmx dt dmy dt dmz dt. Those are just the components of this left-hand side of the equation of motion, and they're just going to form a vector for me. And they're going to be equal to, you can do something interesting here, and you'll see how this bears out in just a second, but we can write this cross-product term on the right-hand side as a determinant. So you may or may not have seen this before in terms of writing things out this way, but the cross-product itself can be written as a determinant matrix. And we just have to have the first vector components, which is the mx component, the my component, and the mz component. So that's just this vector plugged into here. And now we need to also include in the last row, if you will, the components of our B field. So what should I write? What should I write for my first entry?
0.
Yeah. 0. Second entry?
0.
0. Third entry?
B not 0.
0. B not. Perfect. Okay. So now I have something that I can sort of work with a little bit more, and I can write out now individual differential equations. And by that I just mean I can write dmx dt is equal to something in this determinant, right? Do you guys know how to operate out of this determinant expression? You take the I direction, right? That's the direction we care about right now. I take the product of, I need a gamma, right? My gamma from here. Sorry. Is that fair? Don't miss the gamma. Now I just want to operate through this determinant to get an expression for my first differential equation. And so along the I direction, that's just gamma b0 times my minus 0 times mz. So a very simple expression, just my gamma b0. Is that a familiar mathematical concept? Mostly nods. Okay. So I'm going to write my dmy dt similarly. I just get it out of the determinant matrix along the j direction, and I end up with 0 times mz minus an mx gamma b0. And then the last one is just what happens to dmz dt. And what do I have? Just 0. Nothing too interesting. So on these expressions here, if you look at it, those actually form a system of first order coupled differential equations, right? So I have coupled first order ODEs. What do I mean by coupled? My mx term here depends on my my, and my my, time rate of change of my, depends on mx. So they're coupled. They're first order because they're just with respect to time once. It's not the second derivative, it's just the first derivative. And these are ordinary differential equations, no partials at this point. On the left hand, or sorry, on the final expression down here, obviously it's not coupled, so that's nice. It just sits by itself, meaning that the z magnetization just behaves independently. It does things independent of what x and y are doing. And that's going to be really relevant sort of as things go. And in fact, it's not even a function of time, right, for this simple expression. Now, you have to remember the conditions that we're talking about. We're not quite talking about the real NMR experiment yet, right? We're talking about free precession without relaxation. And in the absence of relaxation, your Z magnetization just doesn't change. It just is what it is. The X and Y magnetization, on the other hand, we're going to see in a second, they'll result in precessional behavior, or observable precessional behavior. What we have to do is work with this set of differential equations. And what I want to do is take the time derivative of both sides, and that'll let us decouple these expressions. So we'll go from having coupled first order differential equations to having uncoupled second order differential equations. That's pretty easily done. All I have to do is differentiate with respect to time. So I have dmx squared over dt squared. The only thing I have is the only thing that changes as a function of time is my. So I have gamma b0 dmy dt. And similarly, I want to take dmy squared dt. I'm going to take the time derivative of this expression here. So I have minus gamma b0 dmx dt. So that helped a little bit, and what it really helped is that now I can make a substitution into either of these terms, right? This term here, I have another expression for, and this term here, I have another expression for. They're the first order expressions that I had. And so I'm going to keep the left-hand side. I just have that dmx squared dt squared is equal to gamma b0. But now, where I have my dmy dt, this is where the uncoupling occurs, so to speak. I'm going to have a minus mx gamma b0. So I'll put a minus sign out in front. I'll square this thing, and I'll put in an mx. Make sense? I'm just substituting in these expressions here. I can do it for this expression too. So I have my dmy squared dt squared, and that's just going to be equal to minus a gamma b0 squared my. So what's great about that? Well, now I just have two second order ODEs. And they're not coupled. So that means I can, in principle, come up with a solution to this expression on the left-hand side, and I can come up with a solution to the expression on the right-hand side. And ultimately, they're tied to each other because we know that the system is coupled from the get-go. This is just a mathematical trick and helps us get at solutions. So what do we do when we're trying to find a solution to a differential equation? What's the first thing you always do? We have to guess, right? We always guess at the form of the solution. We say, oh, if I differentiate twice, I need a function that when I differentiate it twice, it kind of looks like itself. Is that an exponential function? No, because that's not going to work. Is it a sine? It could be a sine function, okay. If I differentiate sine twice, yeah, I get back something like a sine. Differentiate cosine twice, yeah, I get something like a sine. Okay, fine. So I'm going to make a guess, and then we're going to solve for some things. But I'm going to guess that the x component of my bulk magnetization is behaving something like a cosine gamma b0t plus b sine gamma b0t. Now that's good. That's a fair guess, but the problem is I don't know what a and b are, so I got to figure out what a and b are going to do. And to do that, I need to state something about the system itself, right? So let's go ahead and let, for example, define some initial conditions. I'm going to say that mx at time t equals 0. We're going to call that mx superscript 0. Just some initial condition for x. And we'll keep doing that for the other components as well. And this will be handy nomenclature. We'll use this a bunch because it's a little bit more compact to call it this way. And we'll do it for mz as well. Okay, that's easily done. We could write this as some vector quantity. We could call m some m0 vector, and it would just take on all of these components. Now, the nice thing about MATLAB is it deals with vector quantities very fluidly, and that's one of the reasons that we'll use it for this course. And I'll show you some examples of sort of doing matrix and vector operations today for working through some examples. So where are we headed? Well, we want to figure out what are A and what are B, so that we actually have, at the end of the day, an expression that says this is how the MX component behaves as a function of time, this is how MZ behaves as a function of time, MY behaves as a function of time. And we can do that now that we've defined some, albeit arbitrary, initial conditions. So let's go ahead and say mx at time t equals 0. If we actually use that expression, we have something like a cosine gamma b 0 times time, which is 0, plus b sine gamma b 0, 0, right? That's the amount of time we're talking about at time t equals 0. And so we have a term that looks like sine of 0, and we have a sine of 0 is 0. We have cosine of 0, which is, so this whole expression just collapses to a. And we already know that this is also, by equivalence, our initial condition, right? Just from here. So that means we just have a better way of describing what is A. It's whatever our initial condition is. So, okay. All right, I'm going to do this again. Let's take that mx expression that we just wrote, that sort of general solution, and differentiate with respect to time. Again, we're just trying to figure out what the heck is mx as a function of time in the most general sense. If I do differentiate that general expression that I have, then I end up with minus a times gamma b0 sine of gamma b0 times time plus b, differentiate sine to cosine, gamma b0 cosine gamma b0 t. Remember from previously that we said, I'll say recall, we said that dmx dt, when we were looking at the coupled forms of the expressions, was equal to my dot gamma b0. Why does that matter? Well, now we have an equivalence of our general solution in terms of dmx dt and my. So this is effectively an expression for my. We can say my specifically at time t equals 0 is just equal to minus a sine gamma b0 times 0 plus b should be gamma. Oh no, yeah, the gamma b0s drop out. The leading ones do. Cosine of gamma b0 times, times 0. So specifically evaluating m of y at time equals to 0, what's this first term? Just goes to 0. What's the second term? Louder? Yep, just b. So what does that mean? Well, it means now I have that b is equal to my. So I defined here, I evaluated this expression, right? My at time equals to 0. That is, by definition, my initial condition, and now I have a value for b. Why is that all interesting? Well, I really wanted to solve for a and b, so I could write the expressions for my different bulk magnetization components. And what you're left with then is being able to write, for example, that mx as a function of time is equal to mx0 cosine, should be gamma b0t, gamma b0t, plus, and here's where the coupling sort of shows up again. It depends on the initial condition for your Y magnetization, times sine gamma b0t. You can work through the same thing for the my magnetization, starting from, say, just this expression here. We know what A and B are. We solve for B here, for example. We solved for A earlier. And so we get a very similar but slightly different expression for our my component. And it just looks like minus mx0 sine of gamma b0 t plus should be my0 of cosine gamma b. So here, what this means is we can describe the mx component of our magnetization once we know some conditions. We have to know what's the initial x component, we have to know what's the initial y component, and then we have to know something about the system itself, gamma and b0. And then we can describe the components of the x component, if you will, for all time, right? Similarly for my, mz was a little bit less interesting, right? Because it just said that dmz dt was equal to 0. We can integrate up from that and say that our mz as a function of time is just some initial condition. Okay. Now remember, this is all in the absence of relaxation, right? So this is, most specifically, this is, again, it's free precession. It's the laboratory frame. And it's without relaxation. Okay? If you didn't catch all the steps, that's okay. We're gonna spend more times on using the solutions rather than sort of deriving some of these solutions, but for the next couple of lectures, we'll still be working with some differential equations. So if you didn't follow that, I would definitely go back over it before the next lecture, because we'll keep working in this sort of ballpark for a couple lectures. Now, there's different ways to do this. What we have here in the end is just an expression for the different components of the magnetization. We're treating it as components rather than vectors. But when we're working with things like MATLAB, sometimes it's really nice to go back to some kind of vector notation and work with these things sort of collectively or all together. And that's pretty easily done. We can just form a vector out of this, the first components here. So this is just my mx as a function of t, my my is a function of t, and my mz is a function of t. And now what I want to do is just form a matrix multiplication that ultimately gives me the same system of equations, but is formed by a matrix operating on a vector. And the vector that I actually want to operate on is just my initial condition vector. So this is just like mx0, my0, and mz0. So it just follows, and you'll see it in a second, that from this expression on top, we can write it in matrix form, and it ends up looking a lot like a rotation matrix, which should make sense to us. We should be rotating at the Larmor frequency, or something like gamma b0, about the z-axis as a function of time. And so I can just write cosine gamma b0 times time. I can write sine gamma b0 times time. This ends up being a minus sine times gamma b0 of time. This is cosine gamma b0 times time. I didn't leave myself enough space. Sorry about that. We'll fix this in a second. What are my components on the bottom? That's 0, and that's 0. And what I left out and really belongs inside here, there's a 0 here, a 0 here, and what's my last value? 1. Just a 1. All right. So sorry, I should have written it like that. What's the point of doing that? Well, it just ends up being a slightly more convenient notation, especially when we go into MATLAB. And I'll show you some code for this a little bit later. In the Lauterbur book, he makes, and I try to stick with this nomenclature as well. We talk about this this is just a rotation matrix, right? And specifically, it's a rotation about the z-axis. So everything that's happening is projections onto the xy plane. So we write it as a rotation subscript the z-axis to tell us the axis about which we're precessing. It depends on gamma b0 times time, how much you've precessed. You precess more if b0 is higher. You precess more if more time has elapsed. And we can just write that rotation matrix. You already have it. I'll write it quickly as cosine gamma b0 t sine gamma b0 t 0 minus sine gamma b0 t cosine gamma b0 t 0 0 0. A nice simple matrix expression for what's happening to our bulk magnetization. Now, it really is from here that we see the Larmor expression showing up, right? And so the frequency at which the spins will be precessing about the z-axis depends on gamma b0, right? So Larmor just said, hey, let's just say the frequency of precession equals gamma b0. So you could rewrite that expression if you wanted to in terms of omega, but that's really all there is to sort of seeing where the Larmor expression actually comes from. You can go back and write this in a more specific vector notation and say that the angular frequency vector is actually equal to minus gamma times b. There's a left-handedness to the behavior of the system. And more specifically, we know what our B field typically is in MR. It's just B0 along the K direction. So these just form different sort of expressions, if you will, for the Larmor equation. And really, it's this one that's the most general and perhaps the most useful, that middle one, right? Because then once you've described what your B field is, then you can specifically say what your angular frequency vector looks like. It's not necessarily a rotation about the z-axis. It could be a rotation about some arbitrary axis, depending on specifically the applied B field. Okay? So I think, yep. Are there questions about sort of the steps that we took or where we ended up? The main point was to draw out this last expression here, that it's by solving the equation of motion, laboratory frame, free precession, without relaxation, that we can observe this Larmor relationship, the Larmor equation. Okay. We'll come back to the slides for a little bit, but maybe, yeah, why don't we take a quick break? We'll come back at like 2:20. Okay? Restrooms, water, whatever you need. Yeah, it'll be, I mean, everything's going to be online, ideally. So if it gets recorded, all kind of stuff. And the slides are usually put up but no, I appreciate that. And I would say just like go over the material, have a look, ask the students. Cool.
Maybe this will become a regular thing.
Yeah, that's okay. I'm totally okay with that.
So this might be more of like a much deeper conceptual question than I realized, but like I understand Zeeman splitting and how it works and how there's a slight difference. My question is, since these things want to get to the lowest energy state, why are there any in the higher energy state going there in the first place? That's the thing that doesn't make sense to me.
That's a great.
Why should there be any in the other state?
Yeah, you know, and I don't know enough at the quantum level to be able to answer that.
Do think any of the suggested readings might have something that explains that?
No, I link in today's lecture. I linked to one. I linked to a paper that says is quantum mechanics needed to understand R or something like that. And the message is basically like no, and there's a lot of like bad explanations for quantum effects in R, and none of this really matters. Probably there's a Malcolm Levitt quote that probably gets into this. I love the detail way beyond me. It's called Spin Dynamics. I have a copy. You're welcome to come by and check it out. I'd love to know the answer. I just don't know. I'm not trained as a physicist. So I don't have a good answer to that.
Yeah, it's mostly just
no, it's a great
I
question.
always whenever I'm looking at new material and things where energy is involved, I immediately think of it in terms of things want to go to the lowest energy state.
Right.
And how does it go from there? And this sort of is like, yeah, sometimes they don't. Doesn't make sense why.
Yeah. That's a great question, but I don't have a good answer.
Okay, well, some other time.
We'll figure it out. I have a question on the last derivation of the why this negative sign in the Lamarck equation.
Where does that negative sign come from?
I usually see the Lamarck equation is not in the vector form because there are two possibilities.
Yeah. There's not two possibilities. I'm not sure what you mean.
Like splitting in the positive direction and negative direction.
Yeah, but that's splitting. Like none of this has anything to do with the quantum, right? Like
yes,
this is all just like how does the bulk magnetization behave in the presence of this sort of field.
Yeah, so normally the direction of the rotating is the same as the magnetic field. I'm not sure where that negative sign is coming from.
Yeah. I don't have a good answer. I just know that I mean, this is the expression that we always sort of see, but it's just like a magnitude expression, right? Because it doesn't say anything about handedness.
Yeah.
And this is the negative sign there that introduces sort of like the concept of handedness, if you will. But I don't have a good answer for that right now. Let's think about it. Sorry. All right, guys, we have just not a lot more material to get through, but a little bit more material. So go ahead and take your seats. Tell your last joke. Have your last snack. Wash your hands. Okay, so this is where we sort of ended up. We had free precession in the laboratory frame without relaxation, right? And I hate to sort of, I've said that catchphrase like 9 times, but it's going to be important that you can make distinctions between these different cases because they're applicable under different circumstances, if you will. And what we ended up with was just an expression here that this is a rotation matrix expression for effectively how the x and y components are changing as a function of time. Then we can see that the z component doesn't really do anything especially interesting. And it sort of drops out of this expression that Larmor said, well, let's just call this precessional frequency here the Larmor frequency. That'd be a nice thing to do. My name's Larmor anyway. And we'll end up with an expression like this. This was our starting point, right? So we said that we knew the equation of motion for the bulk magnetization, write out a determinate expression, end up with a set of differential equations, and work with that set of couple differential equations so we could work towards a general solution. And that was really kind of the last thing that we did is we had a general solution. So we didn't know a specific solution because to describe a specific solution, we have to have very specific, say, initial conditions, right? And so we had some expressions that said, oh, mx depends on, mxy as a function of sines and cosines, but that was still yet a general solution. And I want to look at a very specific solution with you guys. And so paying attention to sort of just the last 3 things first, these are the expressions that we ended up with, right? It told us that the mx component of the bulk magnetization depended on the initial x condition, the initial y condition, and then was a function of cosine and sine. and the my was similar but had some different signs and cosines and negative signs and whatnot associated with it. And that under these conditions of no relaxation, mz as a function of time was just a constant. And so now we're going to do our first experiment. We're going to work with our very first pulse sequence diagram, and we'll work with a bunch of these during during this course. I should have written this a little bit differently. The one should just be specifically underneath this here. Let me just fix it real quick because then it's fixed for all posterity. There we go. So what am I diagramming here? What I'm diagramming is what's the radio frequency activity that we're going to concern ourselves with right now. So imagine that we have a bunch of spins, we've placed them into a B0 field, and at equilibrium, there's nothing interesting happening, right? They're just at equilibrium, pointing nominally along the plus minus z axis, if you will. And now we want to perturb the system like discretely. We want to perturb it quickly. And then the equations of free precession here on the bottom will tell us how do the x and y and z components evolve over a function of time. And the condition I want to talk about is using what's called a radio frequency pulse. We'll talk about how pulses are generated and their sort of mathematical features a little bit later. But right now what I want you to picture is the bulk magnetization points along the z-axis, the bulk magnetization points along the z-axis. And now I'm gonna use some radio frequency energy that's on resonance. It's matched to the Larmor frequency of the spin system, and it's gonna, if I use the right amount of energy, I can tip the system over into the transverse plane. I could tip it all the way into the transverse plane, or I could tip it partway into the transverse plane. And the expression, the sequence of events that we're going to work through right now is just partially tipping into the transverse plane. And so these are general expressions. Now we want to work through a very specific set of circumstances where the RF pulse tips the magnetization. The initial conditions then before the RF pulse would look something like this. So before I've done anything to perturb my system, I don't have any transverse magnetization, not any net transverse magnetization, and I don't have any net Y magnetization. Everything's just pointing along Z, if you will, where the bulk observed magnetization is. Along the Z-axis, things are a little bit different, and I can describe them in slightly different ways. The initial condition for my Z magnetization, sometimes I just call M naught. This is something like the thermal equilibrium value of the magnetization. It's the magnitude of my bulk magnetization at equilibrium. Sorry, this screen appears to really interesting picture. Okay, maybe it's back. We can actually work out, there is an expression, this is in the book, this is equation 339, which falls out of the sort of the quantum physics of all this. There is a way of calculating the available bulk magnetization in terms of its magnetic moment. And it depends on things that we would expect. It depends on B0. It depends on the number of spins that are available. Depends on the temperature, for example. We won't really work with this expression. It might show up in the homework. But there is a way of sort of calculating the available amount of bulk magnetization. Usually we just call it M naught. We just say there's some available bulk magnetization, whatever it is, and now we're going to treat that as the initial condition, and then we can look at specific solutions from there. So really we're just going to, for the remainder of this course, we'll just focus on calling the maximum available bulk magnetization just M naught. Okay, so let's switch over here. Last time. Okay, so you've got some of this in the slides already, but I'll just get us all on the same page. So the initial condition, and the way we're going to write this, we're defining some of our nomenclature today, right? The event that we're sort of talking about, I can draw it down here. You'll remember this already, but we have an RF pulse that's happening at some point in time. Doesn't really matter when it is. And I'm just going to label this as event 1. This is your very first sort of pulse sequence diagram. The pulse sequence diagram just tells us the timing of the different gradients and RF pulses that we're going to use during the NMR experiment. And here I'm choosing something very simple. I'm just saying I have very discretely some RF pulse. We'll call that event 1. We could easily have another RF pulse, so it might be event 2, 3, 4, 5. Eventually we'll be working through, sort of long series of these things. And let's just say the RF pulse happens very, very quickly at some point in time. And the effect, just so you know now, the effect again of that RF pulse is to tip the magnetization over partly. So that's the experiment that we're keeping track of. So what we want to talk about, and this is where nomenclature comes in a little bit, I want to talk about my MX component immediately before time point 1. And that's how I'm going to write it. Okay? So the superscript tells me what event I'm talking about. And I'm talking about what's the state of things immediately before, at time 0 minus. So what is my MXY immediately before some RF pulse? Again, this is spins sitting in a B0 field. What's my MX? Just 0. Easily done. We'll do the same thing for MY. MY, time point 1, immediately before it. A little clumsy, but it's descriptive at least. What's MY? Just 0. Do the same thing again. MZ, time point 1, immediately before it. And what's that? Slightly different things that I could write. I could write it as MZ0. That just means the initial Z component, whatever it is. If the system's truly at equilibrium, then I would usually prefer to write M0. And that's the maximum available bulk magnetization. Cool. So that's not so interesting. What's interesting is what happens, say, immediately after an RF pulse. And I'm going to call it a 90-degree RF pulse. We'll get to this more in the next lecture, but by 90 degrees, I just mean I have bulk magnetization, and I'm going to tip it down into the transverse plane. I'm going to rotate it by 90 degrees with the right choice of RF pulse, if you will. So now I can talk about my MX component at time point 1, but it's now immediately after my RF pulse, right? So there's a couple options here. I'll let you guys in on the way that I've chosen to do it for this particular problem. I can actually tip my magnetization in different ways, right? I could tip it to lie along that direction. I could tip it to lie along that direction. Let's just, for simplicity today, say that I put all of my magnetization along the X direction. Okay? So that necessarily means something about my MY magnetization. How much MY magnetization do I have now? 0, right? I put it all along the X-axis, so there's nothing to be put along the Y-axis. I could have flipped those. I could have flipped it along minus Y in between. Anything's possible. And then I still have to write my MZ magnetization. So my MZ at time point 1 immediately after the RF pulse, what is that?
0.
Also 0, right? If this example seems too simple, that's fine. We'll make things difficult enough as we go. So then the question is, what we really want to get at is what is the behavior of the bulk magnetization MT after the 90? That's the sort of what's at stake here. And we know what that looks like already. We know that the bulk magnetization as a function of time is just equal to RZ gamma B0 C. That's the precessional operator that tells us what's going to happen to our bulk magnetization when it's freely precessing. That's the matrix operator. The matrix operator has to act on the state of our magnetization. And the state of our magnetization is just our M vector at time point. Sorry, that should be 1, 0. So I'm gonna have a shouldn't be a dot product really. It's matrix multiplication. I have a rotation matrix here that's changing as a function of time because I can feed time in as a variable, but it has to operate on the state of my magnetization immediately after that RF pulse. And so what does that look like? Well, I could write mx as a function of time, and y as a function of time, and z as a function of time. These are strung together as a vector. I know what my precessional operator looks like. I had that before. So it's cosine gamma b0 t sine gamma b0 t 0 minus sine gamma b0 t cosine gamma b0 t 0. Rounding out the last row is just zeros and ones. And now that has to operate on the state of my magnetization after my RF pulse. And what's that? What's the first component? What is it? M naught. Second component? 0. Third? 0. Right? Easily done. So that's a matrix way of writing down the sort of system of equations that describes the bulk magnetization behavior. You can obviously break that out as individual expressions. So what's happening to mx as a function of time specifically? That's just cosine gamma b0 times m0. So we just end up with m0 cosine gamma b0 times time. That is the matrix multiplication of this precessional operator and the state of the magnetization that I had. I have my my as a function of time vector. And what is it going to be? Anyone? I'm just going to do the matrix multiplication of this array. I'm trying to figure out what's my y component, right? So my matrix multiplication for the x component here, right, was just these components times this. And now for my my component, it's these components. Circle this one. Draw a line over the other one. So now I just have what? Minus m0 sine gamma b0. Drifting off notes. And then the last thing is mz is a function of time, so I just need to figure out what's the matrix multiplication of these guys on my column vector, and what do I get? A 0, right? So we knew that mz wasn't doing anything interesting under these circumstances. And so what we see, and you can easily plot this out, these are just, mx is just precessing as a cosine, my is precessing as a sine. The magnitude of the magnetization in this case is preserved. There's no relaxation effects to take into consideration or anything like that. So one of the last things I'll show you is just how we would actually sort of affect this in some MATLAB code. And then I can't remember what else is in the slide, but we'll close to rounding things out certainly. So again, that's just a specific solution, right? We had the general solution where we had some initial condition variables flying around. And now we said, well, let's do something to the system in the form of an RF pulse. What happens to the system thereafter? This is code that I put up on the web. You're going to need this later. You don't need it today, per se. And I'll just talk you through it a little bit. I'm just defining a function. PAM is just principles and applications of MR. So I have a bunch of PAM functions that you guys are going to see to get sort of during the quarter. This is our B0 operator. It takes as inputs gamma, B0, and DT, just like the matrix expressions that we've been working with. If you don't hand it any arguments, it defines things for you. It defines gamma, B0, and DT. That's what this nargen means. If the number of input arguments is 0, then define some things. And then we're just going to initialize an array. Now, something that's not obvious yet, but we're going to work, the matrix formulation that I've used so far has always been 3 by 3, operating on 3-element vectors. There's a reason later, and it's related to relaxation, that we want to adopt this 4 by 4 formulation. So don't worry about it right now. It's just some placeholders, effectively. But what we're able to do then is define a B0, this processional operator, if you will. We define it as a 4x4, that it has enough time points in it, that it is a long enough array to cover the time points that we're interested in. We're just initializing it here. And now I'm going to loop through forming a bunch of different B0 processional rotation operators, if you will. And so I define my dw, it's just 2 pi gamma b0 dt. And then this is where the meat of it is. This is just that collection of sines and cosines that tell us what is the specific rotational operator that will act on the bulk magnetization. And so this last expression here is just tied to this matrix expression we've been using for the general solution, and then more recently the specific solution. And this is coded up in MATLAB. What can we do with this? Well, here's another function that's also linked up to the web today. Here we maybe want to make an observation of the free precession. And so we can define some variables again. We can define gamma, operational B0, time steps. All this stuff really matters. Like when you work with, when you get to coding your own examples, you have to pick your time scales and magnitudes well. Otherwise, you won't be able to see things, be able to see interesting things. So this example works out well, but be very mindful of like the delta time steps that you use and the magnitudes of fields that you're using. You can miss the interesting stuff if you don't pick them appropriately. That's part of the trick of working through your assignments. Here I came up with an arbitrary initial condition. I said I had some magnetization on X, nothing on Y, something left on Z. Initialize an array, and then let's just have this B0 operator act on my magnetization. And so this expression here, this looping structure here, is just giving me the evolution of my bulk magnetization vector as a function of time by using that rotational operator to act on the bulk magnetization from the previous time point. So we do this in the iterative sense when we're programming. There's different ways to do it, but this will be useful for this class. So the bottom line is this is my bulk magnetization vector. I'm looping over that bulk magnetization vector, and each time I loop, I'm rotating or precessing my magnetization a small amount, and that acts on the previous state's magnetization, right? That's the initial condition coming in. I have some state of the magnetization, I precess it a small bit. And what that ultimately gives me is the ability to look at my mx and my and mz components as a function of time. And so here, this is a rotational operator operating on my bulk magnetization vector. I can just plot the first, second, and third components. That's just the x, y, and z components. And I just get a figure that looks something like this. And so I can see that my my mx magnetization is plotted in blue. I know it's a little bit small, but it makes sense. It starts off at root 2 over 2, because I said my initial condition for the x was root 2 over 2. It's going to start at root 2 over 2, and then it's going to precess down to something like 0, and then it's going to rotate down to minus root over 2, root 2 over 2, and back and forth. The y component is going to do something similar, but it's going to start off with 0 magnetization, and then as the mx component is decreasing, or going towards 0, then my my component is going to increase. This is simply just plotting out effectively the sine and cosine components of the bulk magnetization as a function of time. We also plot mz. Mz is across the top here, and of course it doesn't do anything very interesting. We defined it to be square root of 2 over 2 in the very beginning. It doesn't change as a function of time because there's no relaxation for this specific case. The last sort of 10 lines here are just the code that's used to generate a plot that should look a lot like this. Okay, so in summary, in terms of what we covered today, this is where we started. We said we knew something about spin angular momentum, and this is really just borrowed from classical physics. And we had this empirical observation that the magnetic moment was related to the spin angular momentum through the gyromagnetic ratio. We needed to understand the relationship between torques and spin angular momentums, and also torques and magnetic fields. And ultimately, this gave us, through a bit of work, the ability to define the equation of motion for a single magnetic dipole. Now, we don't really care about individual magnetic dipoles. What we care about is the bulk magnetization. So we added up all of the bulk magnetization vectors. and we came up with a slightly different expression. There's an easy way to do this and a hard way to do this. But the bottom line is you have a set of ordinary differential equations, coupled equations, that describe the behavior of the bulk magnetization. We know that in conventional MR systems, this is what our B field is. Our B field, this really should just be just B. We don't really need the sub-zero. It's conventionally defined as B0 along the K direction. There are other MR magnet designs, but this is the one that we'll work with for this quarter. No need to make things too complicated. And then lastly, using this equation of motion and the external condition of a B0 field along Z, we can set up and define a set of differential equations, and then we could work with simple solutions. This is the general solution that we ended up with. And then the last thing we did was we said, well, okay, that's general, but now let's talk about what happens after a specific RF pulse, or what happens after specific events. And what this course is going to continue to do is keep working with these kinds of solutions to differential equations and talk about more interesting situations when we introduce things like relaxation, work in the rotating frame. And the reason that's also important is it completely governs image contrast. We need to be able to keep track of the bulk magnetization to understand the contrast that will result in the images that we're interested in. And this is just kind of the starting point for getting us there. So when we come back on Friday, that's a reminder, we have lecture this Friday. When we come back on Friday, we'll talk more about the B1 field. And the B1 field is the one that tips the bulk magnetization and allows us to go from having bulk magnetization to having transverse magnetization. We got a sense for that today. We'll talk in much more detail about it on Friday. Okay? I'm happy to take questions for a little while up front. Otherwise, I'll see you Friday at 1.